Hello everyone. Binning, Quate, and Gerber got the Nobel Prize in Physics in '86. They invented the atomic force microscope, an extraordinary tool that lets us feel the world at the scales of atoms, revealing details that no other microscope can measure. Like reading Braille atom by atom. It's used in the microchip industry to do quality control, especially when dealing with 3 nanometer transistors. It's used in academia where it pushes the limit of our knowledge of the world. It's even being taken to space. This is how the system looks. The most important part that does the sensing is the cantilever and tip. Since the invention, it's been produced by the microchip industry using silicon wafers. Even though it's plagued with materials related problems, no one thought of changing how we make it. The industry is comfortable with the current production process. The global AFM market is $1.3 billion. 30,000 AFM systems are scattered around the world. 65% are in academia, 35% are in industry. Those are higher end AFMs. Global AFM users are 100K and they're expected to reach 1 million in 2030. Global AFM cantilever market is 400 million. 5 million AFM cantilevers are sold yearly, and the price for standard probe is $60. The price for specialized probe is $500. This is how a fresh probe looks like. This is how it looks like when trying to hold it with tweezers and place it in a holder. This process is frustrating. It's like holding a fragile grain with sand and placing it in a needle hole. If you have a vision problem, forget about it. Many AFM users suffer deeply from this pain. Now, let's say you were successful in mounting the probe in the holder after destroying, of course, 5 tips. You look for the cantilever and it's not there. The frustration. Basically, if you sneeze, it's gone. If I go technical a bit, these cantilevers are brittle, stiff. Measuring biological samples, it's like measuring a water bubble with Thor's hammer. It also takes 20 minutes to image sometimes with some tips. The results look like this due to the drift. And let's say the cantilever survives, the tip breaks 5 minutes into the experiment, and now all our observables don't make sense. And it's mostly because silicon is highly adhesive. When it comes closer to a surface, it snaps into it. Sometimes while scanning, it shatters like glass, and if it survives, it gets contaminated, all of which renders all observables meaningless. We solve all these problems with our polymeric chips. They never break, they scan 150 times faster, they last longer. We have a granted patent and a publication in Advanced Science for this technology. Why we 3D chips outperform silicon? Well, there are several reasons, and I highlighted in red based on the ones based on the feedback, customer feedback. She's 150 times faster scans, they last longer, better mounting ergonomy, most suited for biological applications, resistant to wear, higher resolutions, and the flexibility in the 3D design. In theory, today, we can cover 40% of the market need with one operator. But today, at this moment, we are at 10%, and with five, we can exceed global demand. Thank you.